the test statistics. So we're going to be looking at basically two. We're going to be looking at different test statistics, but we're going to focus on ANOVA and of course the T-statistics, so that we'll be able to know how to conduct this test. Now, in general, when we are looking at T-statistics, we are looking at it in, I think, 4 different ways. We have one sample T-test. We have paired, T-tests. We have 2 sample T-tests when we are assuming that they have equal variance. And we also have 2 sample T-tests when we are assuming that they have unequal variance. So we are going to start with the one sample T-test and see how it is being conducted. So in that case, at what point do we even do one sample T-test? This is an instance where maybe a claim has been made and you want to fact check whether that particular claim is true or not. For instance, somebody has formulated a food formula and has given to kids for, let's say, 1 week, or sorry, 1 month or 2 months or something. And then the person said when he checked the average weight of the kid after they had taken the food formula, it was actually 22 kilograms. And these are kids below 15. Now, another example could also be that somebody can make a claim that the average salary of a typical worker in Ghana here is, let's say, 10,000 Ghana cedis. So one sample T-test is when somebody makes a claim and then you verify if it is true or not. Somebody has made a claim that the average weight of the kids after they had taken the food formula was 22 kilograms. Now, that particular claim become the hypothesized mean, right? That's the hypothesized mean. And so we simply can put that one. We don't need to calculate that one. We just have to have it over there. And then we can now proceed to do the rest of the calculations. Now, the H mean means the hypothesized mean. So maybe let me put underscore over there, and then that will be fine. Now, to be able to do a one sample T-test, you need the hypothesized mean, you need the actual mean, you need the test statistic or the T statistic, you need your degree of freedom. So let me put here, that's my T statistics. Then you need your degree of freedom. And then you also need the actual mean. And then, of course, you need your standard deviation. And the total number of samples that you are working with. These are the stuff that you need to be able to calculate a sample. What is the T statistics? Now, the T statistics, let me show you something. I have already created a formula that can calculate it. So I'll call it one sample T test. So I'm going to do that. It's going to ask me of my data. So my data here is the range. This is the data. So I'll simply highlight the whole of this. And then the hypothesized mean, like I told you, it is here. And that's what I need to do. I'll just close that up and then tap enter. So my T statistic has been calculated. Degree of freedom is the total number of samples minus 1. So I can simply say count, what is it? I'm going to count the total number of values here. That's it, minus 1. and that will give me 19. Then my mean, the mean is actually the average. So the average of that's the actual mean. So we simply close this up and tap enter. The standard deviation is the same thing. Standard deviation of sample variance. Use your tab key and then highlight the whole of this. Then we'll close it up and then tap enter. And then the number of samples is obviously 20. But for the purpose of calculation, you just say count. You use the count function to be able to count the total number like this. Then we tap it and then enter. So that will give me 20. So now to calculate our p-value here, so that we can confirm our test statistics, the p-value is usually equal to the t dot two tail. We're going to use the two tail, that's the appropriate one. And then it's asking of x. The x here is the t statistic that we have calculated. So we simply come and click on this. And then degree of freedom, which is here, we click on that, close it up and tap enter. And so our p-value is 0.002. This is way lesser than 0.05, which means that there is a significant difference between the hypothesized mean and then the actual mean, which means they claim that the average weight after the people had taken the food formula was 22 kilogram is not true, because there's a clear difference between that. So this is how we do it. But the question is, how do we get this t statistic? Because I have already created the function. But let me show you in details how we calculate the t statistic. The t statistic is always equal to you have your mean, the main mean that you have here, minus the hypothesized mean. All right. Then divided by, I think I should use the actual formula. So it's going to be the main mean. All right. So you have your main mean. How do I put it? I want you to see the formula first before you can see how we input it. It's actually the main mean. So I will just type them and see whether we can make sense. Minus the hypothesized mean, all right, all divided by the standard deviation multiplied by the square root of the number of samples, which is n, and that is it. So when we do this calculation, then we can get our test statistics. But the test statistic, I have already created a function to hold it. You see, other than that, now let's calculate the test statistic manually here. It's the same thing. So this is our test statistic, our t statistic. Let me put it as way, like this. And so let's come here. The t statistics is always equal to the main mean. So this is our main mean here, the value here, minus, but I think I should put it in brackets to make it easier. Minus, so it's going to be the main mean here, minus the hypothesized mean. We'll close the bracket. And I said divided by, so we bring our division sign, divided by the standard deviation. Here is our standard deviation, multiplied by, and then I can put by the square root. This is my square root of the number of items. Here's the number of items. So we close that up, close again, because we open two brackets and tap enter. I think there's something I need to add. And so you can check and see. You see that the test statistic we have here is 3.477, and it's the same thing here, 3.477. So that's how we calculate it manually. It's equal to, you can check the formula here, 15 minus 12, sorry, 15 minus 22, it is 22, which is here, divided by whatever that the divided by the standard deviation times the square root of the total number of items, which we have already listed here. So when you do that, you get your test statistic. Then the degree of freedom, I've already shown you how to calculate the rest. And then now you can come and then input your p-value. And then you can get your p-value and then compare it. Once your p-value is now less than 0.05, then you can conclude or you can reject the hypothesized mean that the average weight is not 22 kilogram. So this is how we conduct one sample t-test. Now, because I wanted to be a little bit fast, I decided to create my own function for the t statistics. So each time I am given one sample and I need to calculate, for instance, let me move a little bit to a different place. And let's say that somebody has made another claim that the average salary of a teacher or yes, and then I check the lowest salary is 2,000 and then the highest salary was 5,000. So I can simply say run between like this. So the bottom is 2,000 Ghana cedis and then the highest is 6,000 Ghana cedis. I close that up and return. And so let's populate maybe up to this point. So that's the average salary. So I'm just going to copy and then paste it back. So, but the person said that the average salary of a nurse in Ghana here is 5,000 Ghana cedis. That becomes the, let me move a little bit. So that's the hypothesized mean. So our hypothesized mean is going to be, that's the hypothesis. That's the claim the person made. That is, let's say, 4,000 or something. It's 4,000 Ghana cedis. And so it is left onto us to come and verify. So we've gone to pick any nurses. So let me put on top here salaries. So how many nurses have we gone to check? Maybe I have to count them. So we can say number. So the number of samples that we have. So you simply come and then count, come and use the count function. And then I'm just going to count from here up to that point. Close that up and return. So that there are 20. There are 20 of them. So degree of freedom as well is going to be the count. This one here is going to be the total number, which is here minus 1. It's the same thing. And so that will give us 19. Then we can calculate our standard deviation. And then our standard is equal to okay, our standard deviation is here. And then we simply just have, we calculate everything here. So our standard deviation is there. Then we look for our mean. That's the main mean. And our main mean is equal to average. Then use the tab key. I'm doing it twice for us to see how this works. Close it up and tap. So that's our main mean salary. So what do we have left? We have our degree of freedom, our standard deviation, we have our main mean. So we are left with our test statistic or our T statistic. And then our T statistic is where I've already shown you how to. If you want to do the ordinary way of calculating it, then you can say is equal to the main mean And so it's always good to put them in bracket. So you can say the main mean here minus the hypothesized mean, then close the bracket up, divided by, remember, you have to divide it by the standard deviation. Okay, divided by the standard deviation, then multiply by the square root of the total number. Square root of the total number. So the square root function is there. So we use that of the total number, which is here. So if we have all of that, we close up and close again, tap enter. I think I've missed some place. So our test statistic, maybe if I've not, so we've calculated our test statistic. Now we can now go ahead and calculate our so Q order. And so instead of me writing the whole of this function straight away, what I normally do is I've already created a function for the test statistic. So I will simply just call that particular function one sample t-test. Is going to ask me of my data. And so I prefer that one so that if I forget, and then my hypothesized mean, which is here, then close it up and see that it gives me the same thing. So my test statistic is ready. So what is left is my p-value. P-value. And then the p-value is always equal to t dot d. Then you use the two tail. And then it will ask you of x. And I say x is what? The t statistic, which you have calculated here. Then the degree of freedom is here, which we have calculated to be 19. Then we close that up and tap enter. Our p-value is 0.0 or 0.4, which is way greater than 0.05. So we will therefore fail to reject the hypothesis that there is actually, or we can actually say that, yeah, there is a clear difference. What is it between the two? What is it mean salary? You see, so this is how we do one sample t-test, then in that order. Now, the rest of the other test, we don't have to write all this and then follow up. So for instance, let's check to see if I can come back here again. And then I'm going to remove the whole of this. And let's see if we can now do the test statistic that we know. For instance, so I'm going to come to this point and then say automatic. So let's say the next kind of test we're going to do is paired sample t-test. With the paired sample t-test, it happens when you are measuring one variable at different times. For instance, you have given a food formula to kids. They ate it, but before you giving it to them, you had picked their initial weight. After they have taken the food formula for some time, you come to pick their weight again. You just want to know how much impact the food has made on their weight gain. So in that case, that's a paired that's a paired t-test, paired sample t-test, because it's the same children you are measuring their weight gain from beginning to the end. So you measure the first one, that's the baseline, and the end line. So that way it is paired sample t-test. You get it? So in that case, we want to find out whether the the differences in their average weight before and after they had taken the food formula. Was it was there any difference in that? If there was difference, I would say that the food formula actually was good. If there was no difference, we say no, the food formula didn't have any impact. Then in that order. So to do that, that one you don't have to write any kind of. You just have to come to your data. Then we come to this point, and then look for, you see, t-test paired to sample for me. So we select this one, come and click this, remove all everything that is here. It's always good practice that way, so that And so we simply click OK. So I'm saying OK. So we simply come here, we pick the first variable. So we are highlighting everything up to the end. And then the second one too, we highlight from here all the way to the end. That's the second input variable or the input range. So we added with the headers. So we put the headers label on output. We want the output to appear on this particular cell. So I'll click here and come and select where I want my output to appear. I think it should just appear here from this particular cell going. So if everything is okay, then I'll just click. And so you notice that, okay, maybe I can move it like this. Then I'll press my alternate key and HOI to widen it a little bit. So now let's check to see. The p-value for one tail is actually 0.000, so which is way lesser than 0.05, the alpha. So in that case, we can say that there was a significant difference between the the weight gain or the mean weight before and after they had taken the food formula. And that is it. Even if we go to the two tail, it's still the same thing. Then that one. So we can check that that's for paired sample t-test. We also have instances where you are looking at two sample t-test. The two sample t-test come in two ways. We have equal variance and unequal variance. The two sample t-test means you are picking the variables from two different, or you are picking your data from two different variables. For instance, you want to compare the salaries of nurses and teachers, all right? So let's come here, let's come to this point, maybe remove this and add the salaries of, let's say the salaries of let's say nurses. So I'm just going to put the nurses. And then let's also come to this side and say salaries underscore teachers. Okay, I think that's fine. And then we can also simulate that. And so let's say we is equal to, we're going to run it between 2000 or 1700 and let's say 6000 as well. And then that is it. So we simply fill this all the way up to, so I'm just going to copy that and paste all over again. So now let's come and see whether we can. So what the kind of test we are going to conduct here is not paired. It's not paired because there are two individual different variables that we are testing. We just want to know whether there's a salary disparity, average salary disparity between nurses and teachers, and that's all. Nurses are on their own, teachers are on their own. That's paired, that's two sample t-tests. But to be able to know whether the two sample t-tests are, is it equal variance we are going to use or unequal variance, we need to check that. And mostly, we can conduct what we call the F statistic in the first place to confirm. If you don't also want to conduct the test statistic, you can just come down here, variance, and then you simply highlight from here all the way up to this so that you can get to see the variance. You tap enter, and that's the variance. And so I'm going to remove what's here. So we can check and see that the variance are not the same. So if you check the variance here and then the variance over there, it's not the same. So we are going to use unequal variance, assuming unequal variance because of these two values that we have seen. So we come to our data tab now, come to data analysis two pack, and then we go and look for two t-test, two sample, assuming unequal variance because we've already seen that the variance are not the same. So we simply come to that, and then as usual, we are deleting this, and then and then that is it. So in that case, we are now picking our first input range. The first input range, we're highlighting all the way, don't add the variance to it. Then we come to the second input range, we highlight from here all the way up to this. And then our output range is just going to be here. And then we are good to go. So that's it. You have checked the labels as headers. Make sure you also check that because we've highlighted with the labels. So when we are done, we click OK. And so just alternate key down HOI to fit the. And so now we can check to, and then we realize that on one tail, check the p-value on one tail, which is here. You notice that it is greater than 0.05. Even two tail is even worse. So in that case, we can say that what is it? It is the difference, the average salary difference between workers and then teachers is not significantly different because we can see the p-value is not showing any significance. And then, so that was it. That's how we can also do, what is it? Two sample t-test assuming unequal variance. If you understand how to do this, then the one that we have to do with equal variance is the same, just that you need to select the equal variance. If you had checked and the variance are the same, then in that case, you would have used that particular part. And you can even see the variance here, that they are not the same. And then that is it. So this is how we conduct either one sample t-test, the paired t-test, and then two sample t-test, assuming unequal variance. And mostly it will always be assuming unequal variance because it's not easy to find two samples having the same variance. It's very rare. Now, the next part of other tests we can do is ANOVA. ANOVA is when you are now dealing with more than you are dealing with more than two samples. From three samples upward, if you want to find out the differences in their averages, and you want to know whether the differences in their averages is either significant or is not significant, you use ANOVA. If there are two samples, you use a t-test. But more than that, we use ANOVA. So now let's see if I have some examples of ANOVA. So say I have some here. And then under the ANOVA, we have different kinds of ANOVA. We have one factor, no, we have two factors, and then we have interactive ANOVA. Now, under the one factor, we are saying that, okay, there are different ways of teaching. Teaching methods have been developed by GS or UTAC or any body or university. Now, let's assume this is GS. So method A, method B, method C. Which of these methods are the children able to, to perform well? Or which of these method is much more effective? And so this is the question. Do students taught using three different teaching methods have different average test scores? So you see that the groups are more than two. So we cannot use t-test. We can't use t-test, whether paired or unequal or whatever. We cannot use that. We can only use ANOVA because there are three. So to use ANOVA, first of all, we also have to perform some bit of what is it, analysis. We can find out the averages, we can find out the variance, and then all of that, which is very critical, which is very important. But when we run the ANOVA tool, we can just get it at once. So for instance, if I come to my data here, I can come and then look for ANOVA. So this is single factor ANOVA, like I said. So we simply click on that, and then as usual, I'm deleting whatever that is there. And then for ANOVA, this is where you need to pay attention. For ANOVA, we have only one input range. Only one input range. In this case, the input range are the method A, method B, method C. Don't highlight with the case. And I'll explain that. If you highlight with the case, you are saying that there are two factors. In this case, we are dealing with only one factor, and the factor is the teaching method. You see, and so we simply just highlight from here all the way up to the last part. Oh, okay, I did it at a different place. is supposed to be here, the input range. So the input range we are highlighting all the way up to this point, and then that is it. Now, and the next thing is, how are we going to compare the averages, the average means? Are we going to compare it row wise, or we are going to compare it column wise? Once we have told Excel that the headers are on what is it, on the columns, it means we are looking at group, what is column, what we are grouping by column. So each column is a group. Each column is a group. So in this case, column A is a group, column B is group, and then in that order. So we'll tick our labels. Yeah, the method are the labels. So we have to make sure that the labels what is ticked. Then the output, if we want the output range to still be here, then we say output range. Then we simply click on the cell where we want the output to appear. Other than that, we could just click new worksheet, then the output will appear in a different way. And so now come to think of it. So we are now having our method A, B, C, and then we can look at their total marks, then the average scores that they all have, and then the variance that they all have. That's for the summary. These are things we could have calculated manually one by one. Now let's come and look at the ANOVA. Between groups. So between groups, we can see that we have our p-value is not significant. So what we are literally saying is that we can look at our p-value here. It is actually not significant. And when we look at our F critical as against our F car, we see that the F critical is way greater than the F car. That is also another way to check whether the, what is it, between the groups, there is a significant difference in their averages. There is no significant difference. And then in that order. But ANOVA, when you do ANOVA up to this point, the most important part is how do we know whether method A and B, what is it, was doing better, or method A and C was better, method B and C was better than in that order. Which of the method did well? How do we select that? How do we select the method? We are not able to continue with this because the p-value is not significant, telling us that all the methods are good. We do not see any significant difference between method A, B, C. So in that case, we cannot proceed with what is it, the techie honest significance calculation in order to be able to get whatever that we want. But in other cases, immediately you calculate your ANOVA and you notice that the p-value is telling you that there is a significant difference between the groups. Then you need to find out which particular group is more significant or is more interactive than in that order. So let's see if we have some examples like that, so we can actually go into it. Yes, so I have one example here, and then I'm just looking at the total number of genes that are found in different bacteria as what is it? So we have carriage bacteria, we have pathogenic, and we have environmental bacteria. And then we decided to pick their genes. So this is the number of genes that we got from all the samples that we picked from the carriage, or all the samples that were noted to be carriage, which means that kind of bacteria, they have the AMR gene, but they actually don't express it. So when you see take antibiotic, it is able to cure those bacteria. We also have pathogenic here. They are the ones that cause diseases. We have environmental. Those are the bacteria that are found in the environment, like maybe in the soil or something. So we've profiled their AMR genes, and these are the AMR gene counts, 12, 14, then in that order. How many samples? 1, 2, 3, 4, 5. 5 samples each. And then we want to find out whether there is a significant difference between their whatever. If there is a significant difference between the average number of AMR genes that are found in carriage, pathogenic, and then environmental. I've already done that here, but for the sake of us going through, because Here, I want to go through all the way to how to be able to select which one is better and which one is not better. So I'm going to delete the whole of this, and then I will come to this point and say I don't want any border any longer. So all the borders are gone. Now, to be able to do that, first of all, you need to be able to calculate the average, the average number of genes in each case. So already, I don't have to waste my time on that again. Coverage, the mean number of genes was 14. If you calculate it, that's what you get. Pathogenic, 24. Environmental, what is it? We have 17. Now, the next thing we have, now that we have calculated this, the next aspect of the calculation we need to do is to get our ANOVA and then extract some values from our ANOVA. So let's calculate, or let's do our ANOVA. So I will go to my data tab, come to, and then this is also one factor ANOVA. So I'm going to select the single factor ANOVA, and then I am removing whatever that is here. Okay, then I'll leave the alpha value. And then I will simply come to this point, and then I think we are also grouping by columns, as you can see, and where our output range. So our output range is going to appear from here, and I think that's about all. So we click this. I think there's something missing somewhere. Okay, so check our output range. Then you notice that the summary parts, like I'm saying, the summary part is here. You can see the samples are 5. Then the sums, that's the total number of genes in each case. The average, I've already shown you 14, 24, and 17, and these are the variants. All right, now when we come to ANOVA, we can see between groups, look at the p-value, 1.1 times 10 raised to the power minus 6. That's 0.00001, which is way lesser than 0.05, and which means there is a significant difference in the gene count between the different bacterial isolates that we have. So we need to find out which of them actually are having that kind of difference. So we need to select that particular group and say that, okay, this group is the one that is having more of a significant number of, or this was the difference, and the difference was significant. We need to find out those groups. What are those groups? That's where we have to now go into the Turkey honest significance analysis to be able to do that. So now, to be able to do that, there are some key important information we need to extract from here. We need to extract what we call MSE. That's the mean square error. The mean square error is the same thing as within groups MS. Within group is here. The MS is here. That's the mean square. So what is it? Our mean square is this. And so again, our alpha is 0.05. And then the groups are 3. So our K is equal to 3. So now let me come here and show you what I mean. So our MSC, that's within group MSC, is supposed to be this. These are just arbitrary values that are what I'm showing you. Then our degree of freedom, let's say is 12. Let's say if it was 12, our degree of freedom. And then our number of groups, K3, which is here. Then, but like if I say our degree of freedom is what is it? Is 12. You can see degree of freedom is here within the groups is here. Then we come to the number of groups. There are 3, and then the sample size per group is 5. Now the Q, that's the Turkey's honest. This one is a table. You can get that table online, and you'll be able to extract this value. It's always 3.77 approximately if the alpha value is 0.05. And then, so if we have the rest of this, then we can go ahead and then calculate our HSD. That's our honest significance. I've forgotten the meaning of the D. Then we can go ahead and then calculate this particular value. After we have calculated this value, and to calculate that particular value is actually equal to the Q that we have, here, then multiplied by, let's put into bracket, the square root. So I have my square root of the MSE. The MSE is here, which is this, divided by the total number. The total number. So our total number is here. Then we put that. And I don't know if I have put the formula properly. Yes, something is supposed to have been added. So that will give us 3.37 and then in that order. But I've already also created a function for that. So I will simply call that function. That is always better for me, HSD, which is here. And then it's going to ask me of my Q. The Q is here. Ask of my MSC. My MSC is here. And then it will ask of my N. My N is the total number of size, the total number of samples here, and then I'll tap enter. You see that the values are the same. So now I have calculated my HSD. That's the what is it? The techies, what is the honest significance that I have calculated, which is here. The next thing to do is to now do a comparative analysis. The comparative analysis, or the pairwise comparative analysis, which means we have to get the difference in the mean, the absolute values of carriage and pathogenic. So which means 14 minus 24, carriage and then environmental, that means 14 and then 17. Then pathogenic and environmental, that means 24 and then 17. We are taking their absolute values, so ignore the minus sign. So we come down here and now say carriage versus pathogenic. What the difference? The difference is 10 when we subtract them. 14 minus 24 is 10. Carriage, environment, and then carriage. The difference, absolute value is 3. Pathogenic versus environment, the absolute value is 7. Now, we've already calculated our HSD. The HSD we just calculated, which is here, 3.37. Let's leave it over there. So this is our HSD, 3.37, that runs across. So we now compare, what is the difference? We now compare whatever value that we have here, that is the pairwise differences between each group, and then the HSD. So the HSD, the difference here, if the pairwise differences between each group is greater than the HSD value, which is 3.37, then we can say that particular group, that is, yes, there was a significance. It was significant. Then when we come to the second one, we can see this is lesser than this, so we say no. Significance, no. Pathogenic, 7 is greater than 3.8, so it is yes. So at the end of it, we can say that the pathogenic isolate contains significantly more AMR genes than the carriage isolate. That's one. The pathogenic isolate also contain more significantly AMR genes than the environmental isolate. But the carriage and the environmental isolates do not differ significantly. You see? So check. So if you check, you can actually see the comparison here. So in either case, we are saying that the group that has more, let's say, AMR genes, antibiotic resistant genes, was actually the pathogenic, as you can see it around here. So if we were looking for the bacteria source that contains more pathogenic or more AMR genes, then we should be looking at the pathogenic bacteria, which is way more than the environmental and then the carriage. And so this is how we can use ANOVA, and then we follow through in order to be able to get our results. We select the group that we want. The video has become quite long, so I will leave it here, and then I'll come up with another video, then do the interactive part, and then add other aspects as we go along. So thank you. And this is how we conduct the various statistical analysis. Okay.